Hi everyone, I'm Yi Shao. Here is our paper towards multi-layered 3D garments animation. In this paper, we adopt the simulation-based method to animate garments in more general settings, where multi-layered garments are driven by both human bodies and wind. To support the training of our model, we propose a new dynamic dataset called D-layers, which include multi-layered garments. We introduce both the human bodies and wind as outer forces in our dataset. In previous work, garments animations focus on simplified experimental cases, where single-layered garments are only driven by specific human body models. In addition, most of existing work adopts garment-specific designs, which limits their generalization abilities across garments with different topologies and materials. Consequently, their applicability in real-life cases is significantly reduced. To bridge the gap between the experimental scenarios and real-life cases, we explore the garment animation in more general settings close to real life, where multi-layered garments of diverse topologies are included. Garments are also affected by general forces beyond human, such as the wind. To solve the challenging task, we adopt the simulation-based method to animate garments and represent all objects as unions of particles. Consequently, all kinds of interactions during garment animation can be naturally and uniformly regarded as the interactions between particles, including the interactions between different parts of garment and the interactions between garments and various outer forces. Our method thus is agnostic to different topologies and highly generalizable to unseen cases. Specifically, given the outer forces at time t plus 1 and the current garments at time t, we input the particle states of garments and outer forces to simulate the garment's deformations. The model outputs the future positions of each garment's vertex at time t plus 1. To reduce the number of interactions and the computational overhead, we represent garments by patches, and patches are treated as basic simulation particles. The vertices states are decoded given corresponding patches features. To increase the robustness of our method, we leverage the rotation invariance and additivity of physics systems and propose the rotation equivalent transformation. The key idea is to eliminate the rotation effects and enable the model to learn stable semantics of interactions. To achieve this, we rotate the high-dimensional features of interactions in hidden space to capture the semantics, and transform the learned interactions back to the global space for further aggregations. To verify the effectiveness of our model, we propose a new challenging dataset called D-layers. The key features of D-layers are multi-layered garments driven by both human and wind. In addition, the garment's attributes, garment's topologies, and the outer forces are unique in different sequences. For quantitative results, our model outperforms existing methods with lower Euclidean errors as well as the collision rates. Our layers net also achieves superior performance qualitatively in this challenging task. As shown in the videos, the baselines have difficulties to learn the rich dynamics in D layers due to the design based on linear blend skinning. The garment-to-garment and garment-to-human interpenetrations are more obvious. In contrast, our layers net is able to achieve vivid and realistic dynamics similar to the ground truth. In conclusion, we introduce a simulation-based method called LayersNet to animate the diverse garments represented by patches. We also propose the rotation equivalent transformation to effectively capture the semantics and interactions across different scenarios. Moreover, we propose a dynamic dataset which focuses on the multi-layered garments driven by both human and wind. Thanks for watching.